welcome back to another video. In today's video, we're going to be covering an example in regards to exact ODEs. And then in the following video, we're going to be talking about integrating factors. So in chapter 1.4, we have the topic of exact ODEs, in which we have an ODE that's been written in a certain way, and we can find if they are exact, if they met the following conditions, in which case we have the ODE here, in which whatever ODE is given, we need to identify first the m and the n terms. And if the partial derivative of m with respect to y equals the partial derivative of n with respect to x, then they can be considered an exact ODE. And the way we solve them after is solving for u using the formulas that we have over there, number 1 and number 2. So let's look at this example. We have x cubed dx plus y cubed dy equal to 0. So for this problem, first thing we need to do is identify m and n. So in this case, m, it's equal to x cubed because it's the one next to the x, and then n, it's equal to y cubed. So now we need to test for exactness. So we'll do the partial derivative of m with respect to y, and we will find out that the derivative of x cubed with respect to y. So since x is not a function of y, x are different variables, then the partial derivative of this will be 0. Let's try the second one. So this is partial derivative of n with respect to x. This is partial x of y cubed, and the partial derivative of y cubed with respect to x, it's also 0. Therefore, these two are the same, and this is an exact ODE. So since they are exact, then we can actually solve them. All right, we have proof that partial m partial y is the same as partial n partial x. So that's what happened. They are exact. So our next step will be to solve for u of x and y. And to do that, we're going to be using formula number 1 that we have seen before, that states that m is equal to partial u partial x. So if we rearrange here, we're going to solve for u. So partial u is equals to m partial x. And this is where we get our formula that u, it's equal, u is a function of x and y. It's equal to the integral of m dx. So let's do that. So the integral of m, which is x cubed dx, this it's just x to the 4th over 4 plus our constant of integration. In this case, I'm just going to name it h. And this constant of integration, it's a function of y, because since u is a function of both x and y, and we're only integrating here with respect to x, then our constant must be a function of that other missing variable. All right, so now let's use that second equation. So equation number 2. We're going to be using equation number 2, which says that n is equal to partial u partial y. So then we can write our old n that we had here. So n used to be, or is, y cubed. And then this must equal the partial derivative of u with respect to y. In this case, we already know what u is. We have it here on top. Right, we said that this, everything here, this is my new u. So this will be the partial y of, I'll just put it in the corresponding color so you can see where that comes from, plus h of y. And this, we need to find the derivative of that. So doing this, we then get that we have y cubed, and that must be equal to, so x to the 4 over 4, if we take the derivative with respect to y, that is 0. And then the derivative of h function of y, that will be h prime of y. But that's not what we wanted. We do not want h prime, we want h. So in order to go backwards, what we need to do now, it's then, we know that h prime of y is equals to y cubed. So if we integrate both sides with respect to y, we can get our h. So from here, we get that h of y is then equals to y 4 over 4. That's the solution for this one. So after this, we can then get that u as a function of x and y, it's equal to x to the 4th over 4 plus y to the 4th over 4th. And since we know that according to the beginning, we see that du is equal to 0, we have this in our rules, right? That if du is equal to 0, then u, for it to happen like that, needs to be equal to some constant. Therefore, we can rewrite this. We can multiply times 4. So we can get rid of the 4 on the bottom, and we can get that x to the 4 plus y to the 4 is equal to some constant that we'll just call d. And that will be the solution for this problem. So this is the problem regarding exact ODEs. So let's just do one more problem so you guys can get the logic of this. Okay, so we have this other problem in which we see the instruction, we need to test for exactness, and if it's exact, we need to solve. So once again, let's identify first what the m and the n are. So we push it forward. So m for this one is the 1x to the dx, so it will be 9x. And then the n will be the 1x to the dy, so that will be 4y. And then we need to test for exactness. So we know that partial m partial y will be partial y of 9x. Once again, the derivative of x with respect to y will be 0. And we do partial n partial x. So partial x, the derivative of 4y with respect to x, it's also 0. And since both of them are 0, then we say that both of them are exact. And since they are exact, then we can solve for them. So once again, using equation 1, right? Equation 1, we have then that u as a function of x and y, it's equal to the integral of m dx. So the integral of 9x dx, we are going to get 9x squared over 2 plus some constant. This will be a function of y. Then using equation 2, we have that n is equal to partial u partial y. So we already know what n is. We know that n is 4y, and that it should be equal to the partial derivative of u with respect to x, which, respect to y, which the u that we have already, it's 9 over 2 x squared plus h of y. That's a u. So let's check that we have it. So once again, we have 4y and that's equal to partial derivative of 9 over 2x squared with respect to y. Well, that is 0. And then we have the partial derivative of y, h of y, a function of y, with respect to y is just h prime. So from here, we can get then the fact that h prime of y is equal to, for y, once again, you know that then h of y will be equal to the integral for y dy, which will be 4y squared over 2, or just 2y squared, right? Of course. So we know already what h of y is. So then it's just a matter of plugging it back. Then we know that u of x and y, it's equal to 9 over 2 x squared plus 4y squared over 2. And then that u must equal a constant. So we can rearrange this. We can multiply everything times 2, and we'll get that 9x squared plus 4y squared. It's equal to some other constant that we'll name d. And this is the answer, the final solution. So this is a problem. This is another example of integrating, of exact ODEs, doing a test for exactness, and then solving for this equation. I will see you in the next video regarding integrating factors. Thank you.